Hi, I'm Jeff Wilkinson. It's my pleasure to introduce today's webinar produced by Delta Balustrades and British Standards Institute. We'll be looking at edge protection and barrier systems, which is an important topic that hopefully we can introduce you to and ensure that all our fellow professionals are brought up to speed as to the latest developments and ensure that the necessary safety mechanisms are in place. It's an important topic and one that is particularly close to all our hearts, but one in which you'll find that most people are unaware of just how important these systems are. It's often thought that the barrier systems will just perform as they're expected to do, and it's not one of those things that people take particular care in detailing, and that's something that we want to address during today's webinar. We'll be looking at a range of topics during the course of the day, from the systems themselves, how they're put together. We'll be drawing on some experts' opinions as to how these things can be improved. But we'll start by looking at the systems themselves, and in particular it's my pleasure to introduce Stuart Hubble, who'll be looking at the way in which these systems are actually put together in the first place and what the components are.
I'd like to talk, just say a few words if I may, just to summarise, so we know what we're talking about, to summarise in our own minds what constitutes a barrier. And what forms they take within the built environment, the environment that we all work in. There are many cases where we take a barrier for granted. Indeed, we trust it implicitly, we'll lean on it, we trust our lives with it. So this, as you can see, is a typical balustrade. It guards a drop. In some cases it can be quite high. It'll be fixed, always be fixed to a substrate. And that prevents people from either tripping over the edge, falling through the gaps. It won't be easily climbable, and it'll be sturdy. So a system is only as good as its components. Well, balustrade systems are made from a vast array of different components. And whilst it's possible to create a very professional, neat, sharp-looking system, how do we know that that's all been installed correctly? How do we know that that's been assembled correctly and put together right? Will any of the parts work loose? Will they present a hazard to people that are using the balustrade? We can see here we've got some sort of knuckle types, create awkward little finger traps. Some of the fixings there, they're going to cause snag hazards to people as they bring their hands across it. So what we're looking at putting together is something that's more than just the sum of its parts. Again, it's that holistic approach of the whole system being safe and being able to be used safely. So where do we go from here? Do we take the first option that we see there and just say, make sure nobody leans on the barrier, put a big sign on it saying, don't go near this, it's not going to work? Or do we accept, well, it's a fact of life that, you know, sometimes bad things happen, and just as you look on that second scene there, incidentally, curiously on that one, I don't know about you, but I don't know how the officers, the guys who are investigating that down there are leaning on that, how they're trusting in it. We can't take any of those things for granted. We can't say don't lean on it. We can't say, well, it might work, it might not. We can and we must ensure that whatever we specify, whatever we procure, and whatever we install is safe and it's fit for purpose. The public, the people who go on to use the buildings that we're involved in, are going to be entrusting our lives in our integrity, and we all have a collective responsibility to give them what they expect and more.
So there we have it from Stuart, who's explained in some detail the importance of ensuring that you take a holistic approach and you don't just look at those individual components. But that in itself is probably not enough. You need to ensure that the whole system is actually approved correctly. And when you come to that, you'll find that there are lots of different ways and lots of different standards that are actually bandied about. It can be quite confusing even for a professional to understand exactly what the difference between those is. So let's hand across now to Rob Hine from British Standards Institute, who'll explain those key differences for you.
Huge amount of confusion in pretty much every industry sector that I've worked in, and I've worked in a lot, about what is approval. And the definitions, like, people use all sorts of definitions like approval, tested, verified, certified, accredited. And I think generically, a lot of people think they're all the same thing, which is horrifying to me because they all mean completely different things. So what we try to do is we educate them on, if a client or someone in the supply chain is claiming something, what does that claim actually mean? And then there's a lot of things that I've seen in the past where organizations have made self-declarations about a product or a service where they say that it's compliant to a particular standard. And they'll print it on the packaging. They'll say things like, this product is designed to meet the requirements of BS, whatever the standard is. I love that statement. That's pretty meaningless. But actually, if you're reading it as a consumer, it gives you a degree of confidence. What does it mean? It's designed to meet the standard, but actually when we tested it, it didn't meet any of the clauses because we're not very good at designing. So self-declaration is something that we come across quite often, and we try to educate the consumers and the procurement people and the specifiers about what that actually means and the value it holds. If a product is tested and they provide a test report, what's the value of that test report? People think test reports represent certification, but they don't. So a test report will say, a BSI test report will say, this product meets the requirements of this particular standard, and the samples were submitted on this date. What we're not saying is that anything that was manufactured before we tested it or anything that's manufactured after we tested it will be equally compliant, because there's no verification in there. There's no ongoing audit process. We've never been to have a look where the products are made. All we're saying is they sent us a sample, we tested it and it passed. And there's varying different levels of test report. You can have an in-house test report. Manufacturers have their own laboratories where they test their own products in their own laboratories and produce a test report. I'm not saying that it's not valid. What I'm saying is that internal test reports will be subject to commercial pressure, and it's not in their interest to fail their own product. External testing laboratories have varying different levels of quality as well, where you have an external organisation called UCAS, which is the United Kingdom Accreditation Service. What they do is they go into laboratories and they assess those laboratories against a particular standard, ISO 17025, to make sure that the people in the laboratory understand the standards they're testing to, that the equipment they're using is calibrated, that they have the right equipment, that they're testing to the right standard. And that way, if they meet the requirements of that, they can put the UCAS logo on the test report that they produce. So if you're using test reports as validation of compliance, you should look for a third-party UCAS accredited test report as the top level. Third-party test report, non-UCAS accredited, does not carry the same value because the testing process has not been validated by a third party. There are other organisations over and above UCAS who provide the same function. All the good ones are signatories to the multilateral agreement, which you can find online and cross-reference, but primarily in the UK, UCAS is the one that you will see more often. So testing's good, self-declaration, not good. Testing good, not as good as certification. What's the difference? So I'm sure you're all familiar with the BSI kite mark there. So that is a certification device. We award the BSI kite mark to products or services or processes which have been tested and validated by BSI. Nobody else, no other organisation can issue the kite mark. And the way that it works, Pete Rossington's going to go into this in more detail this afternoon when he talks you through the process for kite mark, but it's far more robust than testing. To get the kite mark, you have to meet the requirements of the applicable standard. So it will be tested by either a BSI laboratory or a laboratory that we appoint to do that testing on our behalf. Most of the time they'll be UCAS accredited. If they're not, we will assess that laboratory ourselves. We will then inspect the manufacturing site wherever it is in the world to make sure that they're using quality management systems effectively. So they don't have to have ISO 9001, the International Quality Management Standard, in order to gain the kite mark, but it helps. If they don't, we have to do quite a robust audit of their quality system. Off the top of my head, I can't think of any kite mark licenses we issue which the organisations don't have ISO 9001, but it's generally not a prerequisite. Once we've done that, we bring those two pieces of evidence together and we give them to a certification manager who makes a certification recommendation. So the certification manager knows the customer. He talks to the customer, he engages with the customer. So as an independent organisation, we need to make sure that he is not influenced by that customer. So the certification manager does not make a certification decision. That goes to part of BSI called risk and compliance, who kind of sit in a dark room and don't talk to anyone. They're not friendly people. And they make the certification decision, okay, based on the evidence provided to them by their certification manager. So you can see it's really robust up to that point, like really robust, but it doesn't end there, because once they've received the Kite Mark certificate, they go into the ongoing audit process of certification. And what we're doing here is we are continuously auditing product, which we will select from anywhere we choose within the supply chain, take it to one of our laboratories and test it to maybe not all of the standard, but certainly the safety and quality specific clauses of that standard on an ongoing basis, generally speaking, twice a year. And we will continue to do that until either the customer tells us they don't want the Kite Mark anymore, or we remove the Kite Mark for non-compliance. So Kite Mark certificates themselves actually are only valid for, they're issued on a specific date, and they are valid from that date until termination of the Kite Mark contract between us and the customer. If you wanted to know if the Kite Mark was still valid, there is an online database. At the moment, it's not as user-friendly as we would like it to be, but we're working on that. We're going to consolidate all of our customers into one database, which you will then be able to access and see if that Kite Mark is valid, and then also look at it by product. So you can do that at the moment with the online database that we have for Kite Mark, but it's not that user-friendly. If you would like access to that link of that database, come and let me know, and I'll send you an email link to it. Otherwise, you can find it on our global website if you look hard enough. To talk about Kite Mark and the value of Kite Mark, what that brings, because the standard that we're working to here for balustrades really does address all of the issues of reducing risk, improving quality, reducing cost in manufacture, and improving the revenue for organisations as well. So the 4 key factors we look at when we're designing a good standard. And those values are not just applicable to the specifier, to the manufacturer, the people that have the Kite Mark, but they're also transferable to the specifier as well. Because if they want to reduce their risk and improve the quality of the products and the safety of the products that they're specifying, Kite Mark is a fantastic tool for doing that. If they want to reduce cost, then the Kite Mark is a really good way of doing that, because buying cheap is pretty much guaranteed to be the most expensive way to procure. If you have a product that fails, or a product that's faulty and has to be replaced, it's much more expensive than buying a premium quality and safe product in the first place.
Okay, so there we have Rob explaining the importance of the Kite Mark system and ensuring that when you're comparing these systems, you're comparing apples with apples and pears with pears. It's essential that you understand the importance of the Kite Mark system and just what value that can actually bring to your development. Ensuring that you actually get the safety right in the first place is vitally important. In the next section of this webinar, we're going to take a look at glass and some of the problems in and around that glass. We've got Fraser Caithness of MI Glass now coming up, and he's going to take you through that and perhaps give you some important case studies as well.
A hot topic within the industry at the moment is inclusions, most notably nickel sulfide, although that's not exclusively nickel sulfide, that can cause issues with spontaneous breakage. That is a panel that breaks without any apparent impact or any apparent reason. And the reason why nickel sulfide in particular is an issue in toughened glass is because when we're heating it up and we're creating that tension within the glass, depending on where that nickel sulfide inclusion is within that glass panel, it creates its own area of stress. over time, with heat and various other processes that it goes through, a nickel sulfide inclusion will expand. So during the heat strengthening process, the toughening process, those very small elements of nickel sulfide shrink. We then hit the air with cold air, hit the glass with cold air, and we freeze it in that state. So over time, particularly in facades and external applications, the effect of the sun causes that inclusion to start to expand again, which creates an inherent stressor in the glass. If that stress gets above a certain point, the panel will break. And then it isn't a type of glass as such, it's a process. So one of the ways that we can reduce, and I always say this, reduce, not remove completely. We can mitigate issues with nickel sulfide inclusions. We can't remove them completely. But one of the ways of doing that is to try and replicate some of the conditions that you get on site. Some of those conditions that result in that, what they call the phase transition from the nickel sulfide inclusion going from a small particle expanding to a large particle, is to try and replicate those conditions. So we put the glass into an oven and we're trying to replicate that in a very short space of time. So that if the panel has a nickel sulfide inclusion that is in a particular part of the glass that would potentially cause, well, in reality, if it breaks in the oven, it would have broken on site, we put it into this calibrated oven. Glass is held or soaked for a period of time, and then there's a gradual cooling process. When we open it up, that's when we find out if it's passed. It is a destructive test. If those panels are going to go, they will go in the oven. We will then have to remake that glass. Hence, and more often than not, it will break panels either side of it. Hence why there is an additional cost for heat soaking, aside from all the energy and everything else that goes into it. 2 or more panes of toughened glass. So rather than just bonding annealed glass together, we toughen the glass first. It's additional processes. Again, very similar advantages to standard annealed glass. High degree of impact resistance, remains bonded to the interlayer, and increased thermal stability. Disadvantages, well, increased weight. It's the same with any laminated panel. When you're starting to add in the interlayers, you're starting to increase the weight of those panels. And a 21.5mm toughened laminated panel, for instance, can weigh in excess of 80 kilos, depending on how big it is. So again, it's something to consider in the design phase. Cost. It's more expensive than standard annealed laminate, and it's more expensive than standard monolithic toughened glass. And as I mentioned before, the dangers of the wet blanket effect. So the way to think of it is when a toughened panel breaks into very small shards, they're not able to lock together. So when you've got annealed glass which is broken, which breaks into very large shards, they can lock and they can stop it from bulging out, stop it from moving it. When you've got very, very small pebbles, for want of a better term, with toughened glass, it hasn't got that ability to lock, and that's when it can start to droop. So again, it's just something to consider. An interesting one that I went through was within the city of Toronto in Canada. There's been quite a lot of cases of this in Canada, oddly enough. They had over 25 instances on different buildings of glass falling out into the road below. Now, very similar causes were offered in terms of what happened here with what happened in London. But reading beyond that, I've read a few reports some structural engineers have done, and they really start to say, well, actually, you should be considering the environmental conditions and the way in which the glass panels are fixed. Some of this was balustrade, some of this was facades. And what they were saying is that on one particular building, glass themselves were clamped. And what had happened over time is that glass does expand and contract as it heats up and cools down. You get moisture ingress, rain, those types of things coming in. So those panels had slipped out from the system that they were installed into. Just friction fittings, glass panel slipped straight out, fell onto the road below. In these particular instances, again, very similar to Old Broad Street, a few of the buildings were recladded. Some of the buildings had to have exclusion zones put around them, so they put gardens around the immediate vicinity of the lower floors, so that if panels did fall, they'd only hit the grass and not onto the walkways below. Toronto, there was a couple of other ones in some of the Canadian cities. They've all started to see this. In some cases, there were questions asked of the glass manufacturers themselves, and they will say, well, it's a known risk. If it's a known risk, it's up to you to design in elements that mitigate that risk. The fragility of glass must be respected. Think about its break characteristics, where it's going to go, if, when, should it break. Good design practices. I'm not a designer, but really, I've read a few articles where it said, don't forget the lessons of the past. You know, nickel sulfide. I've highlighted a couple of issues there where we've seen some problems. Don't forget those reminders, those messages. If it needs to be heat soaked, specify it and demand that it is heat soaked. From experience, occasionally you submit a price to a customer. They'll look at it and go, well, it's over budget. What can we do? Well, we believe that specification is correct. You decide what you want to do. And frequently we will have customers come back and say, well, actually, we'll forget about the heat soaking. We'll take the risk. Yeah, sometimes that works out for them okay. Other times they'll end up on the front page of the Daily Mail or, on the news. Ensure conformity to standards and specifications, as I say, fairly standard there. And again, given the company that we're in, we made the decision as a business to go down the Kite Mark accreditation route. We're Kite Marked on our toughened glass. We've subsequently been awarded Kite Mark for our toughened and for our heat soaking process. So we did it voluntarily. We decided that was the way that the market was going, that realistically customers were being more demanding in terms of what they're asking us for, but also ultimately we want to sleep at night. We want to know that when we're saying we're toughening a piece of glass, it's been toughened in accordance with all the standards, it's been tested, been third-party verified, and we know that when that glass goes out onto site, we know it's going to perform the function that it was designed to perform. So we made the decision as a business, and to be honest, it was a great decision to make. Make the same sort of demands of your supply chain. Look at who does their accreditation, what standards have they got, what processes have they got.
So I think there were some really important points that Fraser brought to light there. I think we can see from that just how important it is to ensure that your supply chain is there to protect you as well. In the event that one of these catastrophes were to actually happen, that you've actually brought in the necessary standards, and by doing so you actually drive those forwards. I think we can see from that just how important even minor items like fixings can be, and if we get one of these elements wrong, it can cause a major catastrophe. In fact, we're now going to hand over to Brian Carroll of Masonry Fixings, who will give you another example of just how this could potentially go horrendously wrong and what you can do to ensure that it doesn't happen to you.
The Construction Products Directive became the Construction Products Regulation in 2013, in July 2013, and suddenly we all have to have CE mark products. And the product has to be tested. If it's a fixing, it has to be tested in order to have CE marking. If it's a generic product like a nut and bolt, a 20mm hexagonal headed bolt, then it would probably follow a harmonised European norm, or a HEN, they call them. The harmonised European norms were the old German DIN standards. So there's a standard that says that's the size of a metric bolt. And if you want to manufacture them, you have to manufacture them to this particular standard. And everybody does that, and that's fine. When it comes to fixings, and we'll just talk about fixings, is that the fixings are different depending on the manufacturer. So you might get a 12mm true bolt from 5 different manufacturers, and you line them up on the table. They're all similar, they all do the same thing, but their clip will have a different length, a different size, a different shape. There's different geometry going on. So the fixings are actually manufacturer specific. They're not following any harmonised European norm, and they can't. And a lot of products that are manufacturer specific, that are bespoke products, that are evolving, and there's innovation involved with the products. So they're trying to develop the products the whole time. There's some guy in the back office in Germany, somewhere developing this little thing, and he'll find out that if he tweaks the cone ever so slightly, the performance or the holding capacity of the anchor will improve. His company can then release that as a product, but it won't necessarily happen with all the other manufacturers. And they're all trying to better each other the whole time. So when you have a product that doesn't follow a harmonised European norm, then it has to be tested in accordance with an EAD, a European Assessment Document. The EAD will be a document which will tell you how the product should behave. So again, with fixings, it'll tell you that an anchor can fail in tension, in steel failure, in pull-out failure, in cone failure, or in splitting failure. It's 4 different failure models possible. In shear, it'll be steel failure with a lever arm. If you grout underneath a base plate and you don't tell anybody, and you suddenly move the point of the load, the shear load, away from the surface, you now have a lever arm. So it could be shear with a lever arm. It could be pry out, which essentially, the best way that I find to describe pry out is if you're digging the garden and you put the spade into the ground and you pull the handle this way, it pries out the clay on the opposite side. So an anchor in shear, which has a large diameter and a shallow embedment, could actually pry out the concrete behind it when it's subjected to a shear load. Pry out has to be checked, and if there's an edge anywhere near it, concrete edge failure has to be checked. You do the calculation for all the possible failure models, you pick the one that has the least capacity, and that becomes decisive. And that's what the software will use, or that's what the design model will use. If I've been talking to the Engineering Institute in Ireland, I've been saying, look, we need to adapt this approval system. And nobody actually listened until, unfortunately, there was an accident. And then everybody said, oh, what's after happening? Whose fault was that? Okay, who can we blame? Okay, the installer. Now, he lives in a corporation house. There's no point in going after him. Sure, he has an old banger of a car. That's all he has. Who does he work for? Who's the main contractor? Who's the suppliers? Who's the manufacturers? Where's the big guys that have the insurance? And they threw out the net to see who they could get. They caught me in that net because I had supplied the product. I hadn't done anything wrong. For any of you that have not been in this situation where you get the phone call to say there's been a fatality, there's an investigation, and you're under the cosh. You don't want to go there, guys. It's horrible. It's horrendous. I've been in it. I hadn't done anything wrong, but you feel like you did. You feel like you've got blood on your hands. It's just, that day will change your life going forward, guaranteed. So you don't want to go there, right? And you're not necessarily wrong. You're just now involved in this massive negative investigation, and it's awful. So the animation that I'm going to show you will just help you understand what happened in this particular case. Now, just bear with me. It's a slow animation, but ultimately this is the stairwell, or the stair core, with the wall in place. This is going to run, yeah? Click it again. Okay, so there's the drawings showing you exactly what was going on. And for just ease of understanding, we're going to remove that wall so that you can see exactly what's going on inside. So originally, as I say, this is poured on site. All the continuity boxes are in there. So the connie boxes are in with the rebar inside. After the pour, steel angles were fitted left and right for the half landings and fixed with 3 bolts. Okay? So when that was done, or what was supposed to happen was then that was repeated at every floor level. So this will go a little bit slower because the animation wants to, you see, it's included all the angles the whole way up to the top. This presentation was actually done for the court hearing so that the jury could understand exactly what happened. So afterwards, the half landings are craned into position and dropped down onto the angles. So far, so good. And there's a prop put in underneath every landing and every half landing to assist. The stairs are then located onto the face of the landing. The full landing is then craned in at the higher level, propped, some spacers put underneath it, and the second flight is then dropped into position. Okay, simple enough detail, and this is then repeated the whole way up to the top. So again, landings dropped in, stairs dropped in. It'll just take a second to go through the process. But I think it gives a really good understanding of what actually happened here. So if you're, a housewife, no disrespect, in a jury who doesn't understand engineering or construction methods, this was designed to let you understand exactly what happened, okay? Before we get to the end, it was at the upper ground level, at this level here, there was the failure and everything below it collapsed. And there was a man in the bottom putting in some formwork. So about 40 ton of concrete fell on top of him. And he hadn't got a hope. Okay? So after all of the precast elements are craned into position, the connie boxes, or the continuity reinforcement, is pulled out from the walls. You're all familiar with how that works. There's mesh put in on top of the landing. A bit of formwork dropped in, and the screed was poured to complete the landing. Okay? So that's the process. Again, repeated all the way up the building, and after which time it was all cured, the props were then removed. Okay, so that's simple enough construction. So what went wrong? What actually happened? The design was looked at. The Health and Safety Authority came after the engineer, big time came after the engineer to try and sue him. So the connection was designed considering the permanent condition. So does this have a little light on it? No? Probably does. Anyway, I'll walk. In the permanent condition, when this is all screeded up, all of the bolts are in shear. They're in pure shear because everything is locked tight against the wall, okay? In the temporary condition, there's a gap between the precast landing and the stair core. That then puts a rotation on the angle. So now the anchors are in tension as well as shear. They're in a combined loading situation. That wasn't considered. So what he did was selected 3 number 16mm anchors, which probably would have worked in the permanent state, but in the temporary state, it might have worked. It might have worked whilst eating into the factors of safety that were there. It might not have collapsed. The load was considered as a UDL. I'm not quite sure what disciplines are in the room. A UDL, for those that don't know, is a uniformly distributed load, okay? So when you place the first landing, forget the stairs for the moment. When you first place the first landing, let's just for easiness sake say that landing weighs 6 tonne, okay? It's supported on 2 sides, so there's 3 tonne on each side. It's supported by 3 anchors. There's a tonne on each anchor, okay? Fairly simple. However, when you place a staircase on the front edge of the landing, you're putting a huge point load on this section of the angle. So my understanding, if we take the 6 tonne again, is that you'd maybe have 5 of it, or 4 of it here, 1.5 of it there, and another half there. It diminishes as it goes over the angle. The other thing that, if you were to debate over it all day, you could think, well, actually the angle is trying to rotate, so it's actually in an upward shear at the back. And probably your 16mm anchor isn't going to cope with the loading that's on that front bolt. So probably better to use a 24mm or something like that. The steel angles that were bolted onto the vertical face of the staircase, bizarrely enough, had 24mm cast-in sockets in them. So somebody done the maths on that. And yet on the other side of the connection, it was a 16mm bolt. They're little things you need to sort of maybe think about. That's what the propping was here, guys. The propping wasn't there to hold up the stuff. It was there to help in the event of something going wrong. It was your seatbelt. They didn't put the seatbelt on, okay? So when it did go wrong, it just collapsed like a deck of cards. By placement, I mean the placement of the cranage of the precast elements into position. Placement of precast units must be such that no impact is experienced. When we design connections, we design them primarily for static loads or quasi-static loads. A static load is just a load that sits there and doesn't do anything, doesn't change direction. Quasi-static means it might have a directional change, but it's slow. The element of time it's not like it's fast. So a dynamic load would be something that's beating the whole time. So it's a change of direction of load with a time element to it. Quasi-static or static is just sitting there. These were designed for static loads, as most connections are. They weren't designed for impact loads. At about 3:30, it was a Friday, at about 2:30, 3:30 in the afternoon, the site manager reported that his cabin shook. Okay, the entire site shook. Now, I got access to the book of evidence because I ended up as an expert witness in this really ugly process that I prefer to have had nothing to do with. And in the book of evidence, it said that the site shook, it was reported, but nobody followed up that and said, well, what might that have been? So I would think, and I don't know, and it was never really proven, that perhaps trying to fit a precast unit, which is very tight tolerances, down into a stairwell like that, it could snag. Any of you that are builders will know that. It'll snag and it won't maybe sit, and it'll get stuck in an awkward position. So what you do, you go and you get the Badger bar and we'll free that up and bang, it drops into position. That shakes the site. That shakes the site hut. That applies a massive impact onto the anchors that was never accounted for in any design. Maybe if they had considered the point load on the front of the landing to be the additional weight of the staircase and therefore gone for larger bolts, it may have been able to cope with that. But we'll never know. During the anchor installation, the installer encountered reinforcement when drilling. To overcome this, he used a shorter anchor. If anybody knows how an anchor behaves and how an anchor fails, I mentioned earlier on cone failure, pull-out failure. The cone failure is calculated based on the depth of embedment of the anchor. That determines the size of the cone and how much concrete is going to resist the forces. You reduce the embedment depth, you reduce the cone size, you're going to reduce the capacity. So he did that. He also hit reinforcement and he decided he'd go in at a bit of an angle. We see that often as well with balustrades, funnily enough, where you may have a base plate with an upright coming out from it. And there's an anchor perhaps left and right. I'm not sure exactly how your base plates are produced, but there's an anchor left and right, and there's maybe a 30mm or 40mm gap between the upright and the clearance hole for the anchor. The guy arrives along with a drilling machine, which has a big chunky body on the machine. He tries to drill, but the body of the drill is hitting the upright, so he can't get perpendicular to the base. So he goes in at an angle. Okay? If you go in at an angle, the nut and washer end up skew-ways on the top of the base plate. You then torque it up. You're now bending the whole anchor around by the fact that you're torquing and trying to bring the washer flat onto the base. Okay? That's the sort of thing you need to look out for. Anchors need to be perpendicular to the surface. The drill hole needs to be perpendicular to the surface. Drill bits need to have a PGM mark. What the hell is a PGM mark? I haven't got all day, but have a look. There's regulated fixings, drill bits for fixings. I can drill a hole to put a cable through a wall. It doesn't matter if it's 12 or 12.5. If I want to drill a hole for fixings, it has to be spot on. And so therefore it should have a PGM mark, which is a German regulatory body for drill bits. It needs to be perpendicular to the sides. It needs to be the full depth. If you hit reinforcement, it's unfair. A lot of the installers feel, you know, it's Thursday and I have to get the heck out of here for tomorrow, so I'll drill all around it till I get in. And now he's left this oval-shaped hole with, it's a disaster. He should stop and he should go to his supervisor and say, by the way, the design as you've given me doesn't function because I'm hitting reinforcement. Tell me what to do next. That's what he needs to do for his own safety. But he's feeling a little bit sort of as if he's the man down the end of the line and, you know, I'm going to get killed by my supervisor if I don't get this done. He needs to, and you guys, if you have teams of installers or teams, you need to tell them that. If you can't achieve what you've been asked to achieve, stop and come back to me and we'll find another way around it. Anchors must be selected, procured and installed according to BS 8539. And for me, that's the biggest piece that came out of this incident in Dublin. And that now transfers across into all sectors of the industry. Within the CFA, we're trying to get a CSC card for anchor installers. There's no recognised profession as an anchor installer. Anchor installer could be anybody. You could fit in handrails, you could be fitting facade systems, you could be fitting urinals in the bathroom, you could be doing anything. So there's no proper profession.
Wow, that was a really powerful message there from Brian. I think that really brings home some of the issues that we face. And even if you've gone through the process of specifying the correct products, specifying the correct materials, even having them delivered to site, things can still go horribly wrong unless you ensure that the operatives are trained and are competent to actually do the installation correctly. It's vital that we maintain the necessary standards of supervision on site if we're going to avoid that kind of problem. And it's certainly something that, following Brian's powerful testimony there, I think all of us are very keen to avoid. In the next section of the webinar, we've been granted VIP access behind the scenes here at BSI. So let's go on a little tour.
So this is a test rig that's designed to bend the glass. It has rollers to let the glass move. We cover it in plastic to make sure that it doesn't explode everywhere. And there are set speeds, and we pull it. It's a tensile test machine, and we pull it apart. Do you want to set it off?
So obviously the thicker the glass, the slower the speed. But obviously with this, it's 55 per minute.
Okay. It will make a bang. Okay, so just be aware. The other things that we do in here, we do all our metrology. It's all our measuring, our accurate measuring. We have shadow graphs where we section copper fittings, brass fittings, malleable iron fittings, but we also do a lot of plastic pipe products. So what you'll notice is the glass is bending, and it will hopefully end up bending like a banana before it breaks.
And why have you two rollers and not just one in the centre?
The standard is designed around how they want it to bend, and quite often the standard.
Snap, wouldn't it? It wouldn't bend so much if you had just the centre one. More of a pivot. Also, to extend on what I just said, an assessment is also made between the rollers. That's a safe zone of breakage. Okay. So anywhere outside the rollers, that's unsafe. You know, it's essentially a fail for that one as well.
it does surprise people how flexible glass is. With the 6mm glass, it goes off with a pop. It's quite spectacular to watch the much thicker pieces of glass, but it takes a bit longer. So. This is going to make me jump. Oh, there we go. I wasn't kidding about the bang.
Well, that was a really fascinating insight behind the scenes of the lab tests, and I think that's really started to challenge people's understanding of just what the properties of glass are and how it actually performs. If you get that specification right in the first instance, you can see that glass is really a really safe product to be able to be used. Now let's take that example and let's move it into the barrier itself while we look at a line load test.
In this test, we will apply a 0.74 kilonewton line load to the handrail of the balustrade being tested. This is in accordance with BS 6180 and is the typical loading that this type of balustrade would be expected to withstand. As we can see in the video now, the balustrade is deflecting under load, and the red line shows the distance that it's moved. We've reached a point where the load applied is 0.76 kilonewtons per metre, and the measured deflection of the handrail at this point is 17.8 millimetres. Under the British standard, the balustrade is permitted to deflect up to 25 millimetres, so in this case it is a pass, and the permanent deflection of the balustrade is 0, which means that it will return to its original position when the load is removed.
So it was really interesting there to see the performance of the system as a whole, and I think it really brings home the importance of testing the thing in situ and as a whole. For those of you that whetted the appetite of, we do have a full tour, and if you want to sign up at the end of this, we can give you access to the full tour itself. Having seen just how important it is to ensure that the systems work in their entirety, that brings us on now to making sure that you've got a factor of safety, or that you can guarantee that the final performance is actually going to achieve what you're specifying in the first instance. And almost certainly the best way of achieving this is to go down the British Standard kite mark system. And I will now hand over to Pete Rossington of British Standards Institute, who will explain this in more detail for you.
Where it comes to new kite mark products, this is the process that we take. So we'll start with the standard. BS 6180 is a prime example of that. It's a relatively new kite mark offering. We engaged with industry, we engaged with Delta, and between industry and BSI we've actually established a framework that is going to work for industry. And that's the key factor here. Rather than what we think you want, we've engaged and we've established what's really going to meet your requirements. And once we've taken that on board, we've reached our framework, we can then turn that into a kite mark. Now, Delta were an early adopter of this particular kite mark for BS 6188. It's a great example because it's so new. There was a gap where a manufacturer could have some type testing, they could hand over a type test report. That report could be 2 years old, 5 years old, even older, and that was all that they were handing over in terms of evidence that their product conforms. And as you've seen in the previous slides as well, it requires commitment, not just financial, but it requires a real commitment to the quality of your product, to your processes, to your quality management, to your factory production control, and to ensure year on year at audit, your product is still being produced to meet the requirements of that particular standard. Ultimately, this is what the kite mark gives. The kite mark gives trust. It allows people to have that faith that the product that they're buying meets the requirements of the standard, that it is a safe product, that the manufacturer's commitment to quality is there. And it's more than just a financial investment. It really is an investment in manufacturers to ensure that what they're putting into the marketplace has that seal of quality and is safe.
Thanks for that, Pete. I think that really brings home the importance of the BSI kite mark system and how that builds trust in products. Hopefully today has been a brief introduction for you. It's helped to raise your awareness of all of the various parts that go towards making a safe and compliant system. We've seen just how a system is put together to begin with. We've looked at some of the various components, we've looked at the testing regime, and all of this is vitally important. It's vitally important in particular for anyone working in the construction industry post-Hackett. Now, for those of you that perhaps haven't followed this, the Hackett report has made a series of recommendations about how safety needs to be put at the top of the agenda for the construction industry. Dame Hackett has explained in some detail that we can't just leave this and wait for government to take action. So this is your opportunity today to take some of the lessons that we've learned and look at how we apply these going forwards. So often people will look at regulation and see it as the thing that they have to do. It's a barrier to them. But in fact, it's how you keep yourself safe, it's how you keep people around you safe, and it's how you ensure that lives are protected. All too often people will design down to the minimum standard, and I think we've seen today the importance of actually trying to design up to the highest possible standard, particularly when it's something as important as edge protection. These are life safety measures and something that just can't be left and assumed that they'll be compliant at the end of the day. By looking at the subjects that we've looked at today, we've developed through an idea of what you can actually do, but we've only had a chance to touch the surface. What I would ask you to do is to think about all the lessons that we've learnt today and to take those forward. Here at Delta Academy, we have a huge number of resources that you can sign up for. There are CPDs and there are other webinars. So please, hopefully you've enjoyed this. Now is the time to sign up and get yourself involved and find out more. Thank you very much.